Hello, I am Ahmed, and in this video I'm going to talk about the post-buckling. A cantilever column is assumed to be under compressive load of P, and we increase the load and we check after it reaches to its maximum critical load, Euler buckling load, what would happen. Let's move on. So the question is about the column, fixed support at point A with the height of L, and at point B we have compressive force P, and the stiffness is EI. Now we are going to calculate critical load, and then we can go in more advanced topic for the post-buckling. Eventually we will calculate what is the vertical deflection of point B. We know that total potential energy will be 1/2 integration of EI kappa power by 2 dx from 0 to L minus 1/2 P integration of V prime power by 2 dx from 0 to L. There is another video that we can find out how to calculate or how to derive to these two equations, which is not covered in this example. Now, we can calculate kappa, which is minus V second divided by the square root of 1 minus V prime power by 2 from the mathematics. And now I can multiply this by 1 plus V prime power by 2. It will be minus V second square root 1 plus V prime power by 2 divided by square root 1 minus V prime power by 4. As far as V prime is very small, it's rotation. So in this equation, V refers to displacement. V prime is the rotation. So V prime power by 4 approaches to 0. And from the Taylor equation or Taylor series, we can derive to 1 plus V prime power by 2 will be 1 plus 1/2 V prime power by 2. So there is another video about the Taylor series that you can watch, how to derive to this equation. So kappa will be minus V second times 1 plus 1/2 V prime power by 2. This is the kappa, and we can substitute this to the total potential energy equation. So it will be pi equals to 1/2 integration 0 to L E times I times V second derivative power by 2 times 1 plus 1/2 V prime power by 2 totally power by 2 dx minus P/2 V prime power by 2 dx. Now, to calculate this integration, we can assume after buckling what kind of buckling shape we will have. So we know that the buckling shape will be for a cantilever like the dashed line, and P critical is pi 2 EI over 2L power by 2. We already know that. Now the easiest way is to just determine or find out a function that would resemble to the dashed line. So if we look at the cosinus graph, from 0 to p over 2 cosinus x, it looks like the same pattern as we have here in our column. So I can assume that it is following the same, but I have to make it in a way that the boundary condition at point A is met. So for this, I can write down that v as a function of x is cosinus. So I would like that at the end of the tip, at L, it's the domain. So it should come to p over 2. So I will go with p over 2lx. But as far as in the initial position, x equals 0, it should be 0. I can reduce it by 1. But this is the shape. So we are sure that this needs to be multiplied by a factor because it is not 1 or 0. So it is a portion of that value. So the function is the shape and a is the multiplier or the multiplication factor. So this is the shape that we can assume after buckling the column would buckle like this shape. Now we have Vx, which is a times cosinus p over 2lx minus 1. And to solve it easier, I assume that a is a factor or portion of the total length. So cosinus pi over 2l times x is dimensionless. So this function shape is completely dimensionless. As a result, a should have the same dimension as v, and v is referring to the deformation. So we can assume that a is a portion of the length. Then I can write down Vx equals to alpha L cosinus p over 2lx minus 1. And now I'm going to calculate the pi with this function that we assume. So it is easier if we go to, for example, MATCAD. V is a function of x and L and alpha, and is alpha times L times cosinus pi divided by 2L times x minus 1. Now I can write the total potential energy. It's a function of E, I, and P, also L and alpha. It will not be a function of x because we are making the integration. So it will be 1 over 2 times integration from 0 to L, E times I times second derivative of the function v by respect of x don't forget to write the function power by 2 times 1 plus 1 over 2 times first derivative of the same function power by 2 and power by 2. Now, if I continue writing, perhaps I go to the next page, adjacent to this page. If you don't like it, you can just select the minus sign and then Control Shift and Enter. It will go directly to the next line. P divided by 2 times integration of V prime power by 2. Integration of V prime power by 2. From 0 to L dx. So the concept is the same. If you remember, we went through the rotational spring, for example. We formed the total potential energy, and to calculate the critical load, we made the first derivative by respect of the unknown factor, which here is alpha, for example. And then we found out the second derivative to check if at what point it will be stable. Now the same concept here. First, I calculate this pi and first derivative by respect of alpha. You can also expand this. And the second derivative yes, we have these three. This is the pi function. I will write it down. So pi function will be pi 2 ei over L alpha pi power by 6 divided by 32,768 plus alpha pi power by 4 divided by 1024 plus alpha pi power by 2 divided by 64 minus alpha 2 pi 2 over 16 times PL. This is the pi function. I can bring also the first and second order derivative for this total potential energy equation. So rho pi by respect of alpha will be, now we have ei pi 3 over L. So it will be 3 over 16, 384 pi alpha power by 5 plus 1 over 256 pi alpha power by 3 plus 1 over 32 pi alpha minus alpha pi 2 divided by 8 PL. And if I put it equals to 0, then I can find out P critical. So P critical will be pi ei over L2 times 8 3 over 16 384 pi alpha power by 2 plus 1 over 256 pi alpha power by 3 plus 1 over 32 pi alpha. There is one missing alpha that needs to be here. So I can factor pi alpha from the equation. So P critical will be pi 2 alpha ei over alpha L power by 2. And I can just multiply 8 16384 divided by 8. So it will be 3 over 2048 pi alpha power by, okay, it was 5. Now it is 4 plus 256 divided by 8, 32 pi alpha power by 2 plus 1 over 4. So this is P critical. And alpha can be crossed. So then referring to P critical 0, it was pi 2 EI over 4L power by 2. So if I multiply this with 4 over 4, then I will have 4P critical 0. The same method that we used. So then P critical over P critical 0, that we called it lambda, will be, I can multiply 4 with this equation. So it will be 3 over 512 pi alpha power by 4 plus 1 over 8 pi alpha plus 1. So this is the lambda equation, similar to what we had earlier in the other example. Now the next is to check where this is stable. I will write lambda here that we can compare the results. Three over 512. One over 8. Power by 2 plus 1. So round 2 pi by respect of alpha will be pi 4 EI over L 15 divided by 16384 pi alpha power by 4 plus 3 over 256 pi alpha power by 2 plus 1 over 32 minus P pi 2L over 8. And to check if this is stable, it should be greater than 0. As a result, P should be less than, or P critical in any case should be less than pi 2 and pi 2. It will be 8 pi 2 EI over L2 times 15 over 16384 pi alpha power by 4 plus 3 over 256 pi alpha power by 2 plus 1 over 32. Similarly, we know that this is 4 times P0. So then P critical divided by P0, which is lambda, should be less than. So I can just write down 32, 16384 divided by 32, 500. So it will be 15 divided by 512 pi alpha power by 4 plus 256 divided by 32, 3 over 8 pi alpha power by 2 plus 1. Let's compare these two equations. So lambda here should be less than this function, let's say this is lambda s. We can see that 3 over 512 is less than 15 over 512. So it's less than that. 1 over 8 is less than 3 over 8, and 1 is the same as 1. So we can see that with any pi alpha factor, lambda will be less than lambda s. So the equation valids for any pi alpha value. If we want to sketch it by MathCAD, let's see how it looks like. Lambda as a function of alpha is 3 over 512 times pi alpha powered by 4 plus 1 over 8 times pi alpha powered by 2 plus 1. And lambda s let's call it lambda s. So this is 15. This is 3. Now we can plot these two. We want to start from 0. And here also 0. So it will be lambda alpha, and this will be alpha. And if I just change this to pi divided by 2. So here we can see that, let's limit this value to 10. I can change this trace factor with this style of dash line. So here we can see that it's exactly the same sketch that we had earlier in the rotational springs. If you remember, we sketched with the one rotational spring, and it was more or less the same. And the value 1 shows that, okay, the load comes up to when the lambda is 1, and after that, there are two choices for column. It can continue to be straight, which is unstable, or it can try to lean or move. And here we can see that alpha is showing the same concept. So it's leaning, it's moving, and it is stable because of the bending stiffness inside the structure. Alpha is representing the deformation. So if we come back to the first page, we assume that alpha times L is A. And A is a constant value, so it's a portion of the length. And let's recall it one more time. So V was alpha L cosinus pi x over 2L minus 1. Now if I calculate V at x equals to L, it will be alpha L cosinus p over 2 minus 1. So V at x equals L will be minus alpha L. So we can see that alpha is representing the displacement at the tip as a portion of the length. So it's displacement. In the other way, we had the rotation or delta. So it's related to the same concept. I can write this alpha is the delta at tip divided by the length. So we have the same equation, and I can say that now we are very familiar. So this is the primary, and then this is the secondary path, which is stable. Now the next is to calculate the relation between these two, and to find out how we can, or with what level we can increase the load. Now I can solve this equation by respect of P alpha. So it will be 3 over 512 pi alpha powered by 4 plus 1 over 8 pi alpha powered by 2 plus 1 minus lambda equals to 0. If pi alpha powered by 2 is x, then it will be 3 over 512 x2 plus 1 over 8 x plus 1 minus lambda. And this is a polynomial with the degree of 2. So x will be minus 1 over 8 plus minus square root of 1 over 64 minus 4 times 3, 512, 1 minus lambda, divided by 2, 3 over 512. So first of all, x is representing pi alpha powered by 2. So it should be positive. As a result, if we take negative sign, then it will be a negative answer. So this is crossed, and the only possibility is that we take the positive sign. Minus 1 over 8 plus 1 over 8 square root of, so it will be 1 minus, will be 3 over 2, 1 minus lambda. And I can continue with this. So pi alpha powered by 2 will be 1 over 8 divided by 3 over 256. So that will be 257 divided by 8, 32 divided by 3, square root of 1 minus 3 over 2, 1 minus lambda, minus 1. Now let's discuss about lambda. Lambda was P critical divided by P0. This P0 is Euler buckling load. We found it from Euler equation. And we know that lambda is always greater than 1. We can see from the equation, and also after bifurcating the system, so it starts to increase the capacity, so which is called post-buckling. It was stable in the secondary path. So I can write this. So we know that P critical is greater than P Euler force. So it will be PE plus delta P divided by PE. So it will be 1 plus delta P divided by PE. And I can rewrite it down. 1 minus lambda will be minus delta P over PE. So now I can substitute 1 minus lambda to pi alpha powered by 2 equation. So it will be 32 divided by 3 square root 1 plus 3 over 2 delta P over PE minus 1. And then it will be 32 divided by 3. So as far as delta P is very close to 0, it cannot be 10%, 20% of PE. It will be very close to PE. It's post-buckling. Otherwise, the structure would lost its stability or equilibrium. So in this case, I can use the Taylor series about 0. So it will be 1 plus, I can write the equation. 1 plus x is 1 plus 1 over 2x when x approaches to 0. So it will be 32 divided by 3, 1 plus 3 over 4 delta p over pe minus 1, which is 8 delta p over pe. Now from here, if we make the square root from both sides, p alpha will be 8 delta p divided by pe, and this will be 2 square root of 2 delta p divided by p, or alpha will be 2 over p square root of 2 delta p divided by p. So now, if we come back to earlier discussion, alpha is delta of tip divided by L, and delta at tip will be the maximum value. So I can say that delta max will be alpha times L, 2L over pi 2 delta p divided by pe. So this is the maximum displacement in the post-buckling phase. Okay, now with this delta max, we can calculate what is the maximum bending moment. So delta max is 2L over pi square root 2 delta p over pe. And then this is delta max. So the maximum bending moment will be P times delta max, which is now PE plus delta P times 2L over P square root of 2 delta P divided by PE. And then we can also calculate what is the maximum stress, which is P divided by A plus M divided by W. So this is how we can calculate the maximum bending moment in this section. A second order effect is not considered in this calculation. It is out of the scope. But if you consider that, so it will be more than this stress. Now, suppose that we want to calculate the shortening of the element after post-buckling. So U can be calculated with the equation of 1 over 2 v prime power by 2 dx. I have another video recorded for how we derive to this equation. You can check that as well. Now we need to rewrite V. V was A cosinus pi x over 2L minus 1, and A is representing delta max. So which is delta max times cosinus pi x divided by 2L minus 1. So V prime will be delta max times minus P over 2L sinus Px over 2L. And V prime will be, if I substitute delta max, it was 2L over pi square root of delta P 2 delta P divided by Pe times minus P over 2L sinus Px over 2L. And then I can determine y prime square, which will be, so pi with pi, 2L with 2L. So it will be 2 delta P divided by PE times sinus 2 Px over 2L. Now I can substitute this with the U equation. So U will be 1 over 2 times 2 delta P over PE times integration from 0 to L sinus 2 Px over 2L. So this will be delta P over PE times integration from 0 to L sinus 2 Px over 2L. You can calculate this integration by hand or by MATCAD. So it will be integration from 0 to L, and this is sinus P times x divided by 2L power by 2 x. So it will be L divided by 2, and then we can rewrite the equation of U, which is delta P over P times L2, or 1 over 2 delta P over PE times L. So this is the elongation. Now it's time to have a confirmation and to see how it works in modeling in software, for example, for RFM. For that, let's assume a cross section. Let's go with the cross section of, for example, 168.3 times 10. First, let's calculate P Euler, which is pi 2 EI over 4L power by 2. We can assume that we have a 5 meters column and moment of inertia is 15.64 10 power by 6 millimeter 4, and then the modulus elasticity 210 gigapascal. Let's assume that we are using S355, meaning that Fy is 355 megapascal. So then Euler force will be pi 2 times 210, 15.64 for 5,000 power by 2. So it will be 324 kilonewton. Now, it should be noted that sigma at Euler will be PE divided by A, which is 324 kilonewton divided by the area, which is 4973 square millimeter. So it will be 324, 4973, and it's only 65 megapascal. But we have to notice that if it goes through the secondary path, then it starts to take moment. And when it takes moments, so then the stress will be different. So we are going to use RFM, for example, to check this. Let's go to a new model. And we need to go with nonlinear material and structural stability. I use upward. Hopefully we have the cross section already. Five meters above, and then we have the section. And here we are going to use the fixed support. Let's have the load. I delete this one and I add the load name buckling. And I exclude the self-weight. So here we need to have a new analyzer setting. I go with the second order because we have to check the nonlinear calculation. And here we have the Newton-Raphson with post-critical analysis. Number of load increment, we can go with 100. You can neglect favorable effect we do not have. Check stability based on deformation rate. So it means that it goes and check if the stability needs to be considered and save all the results. This is the setting for this calculation. Also, we are going to use a structural stability. We need it. So here we can go with the increment method. 1 would be fine. And so here we can start with the initial factor of 0.1 and increment of 0.1. Also in the eigenvalue method, we can go with the root. So then if you want to have a little bit beyond the critical, you can activate this, let's say to 1.2, 1.5. And this is the setting. Now we need to apply the load. It was minus 340. So let's go with 380, for example, to see what would happen. Here also we have the calculation diagram. You can activate it. And here you can go with the static analysis or with the stability. For now, I will go with this one. The horizontal axis can be result types, and the other one can be the node's global deformation. We need to select which node we are looking for. That's good for now. The only thing is that if you calculate with this one, then it is completely elastic. But as far as the structure is going to be inelastic, then you need to select non-linear elastic member for the member. So here you can see that, okay, we have the hardening strength elasticity as well. Let's run this. Hopefully we get good results. So here you can see that in the calculation we have this ST3 because we forced it to check stability before calculation. Here you can see that it comes back to ST3 and then SA4. Here you can see that the increment, we set it to be done with 100, and this is the iteration. So 340 is about 85%, 90% of the 380 that we applied. So here you can see that the iteration is done very fast. Up to here, it means that it can find the stability and equilibrium very easily. Now, here we can see that in the 93 iteration, it cannot converge in the iteration, and it goes to the maximum. If we change this maximum iteration to even 500, I don't think that we will have the convergence because it is not. So after that 93, then the results might not be reliable because there is no, it is just 100 times iteration and the results would not valid. And we cannot confirm with our calculation. But with lower value, when delta P is very close to P to 0, then it might be here. You can see that after 93, every time the iteration goes to 100 and it cannot converge, we have to receive some messages about that. Let's see. You can see that none of them could converge because it is not stable. It is not in equilibrium. Yes, we received a message. The message says some errors and warnings occurred during the calculation. Please check the table. So if we come to the errors, the calculation did not converge, but the results might be applicable. I don't think this, in this case, it is. To achieve more precise results, increase the number of iteration or increment. So if we do so, as far as it is not stable anymore, you will see that it is not working. Here you can see that ux perhaps, or uy. So here we can see that uy is 24 meters. It's not happening. And here also, if we go to the calculation diagram for the static analysis, we can see that, for example, uz, it comes up to 1.9 millimeter, which is prior to the buckling. And after that, you can see that it is increased dramatically. For ux, you can see that it goes to 7 meter, and for uy, it goes to 245 meters. So these are just checking that, okay, it is not working. If you go to the stability analysis for the buckling, for uz, you can see that the calculation is done with 85 steps. So 85% of 380 is 323, which is almost the same value. So after that, it is the critical load to calculate. Let's bring this interesting graph to our notes. And then also, if you go to U value, perhaps it is more appropriate. So if you remember, it was about 93, the steps 93. And after that, what the factor was about 85. So from step 85 to 93, this is the delta P that it is stable and in equilibrium. So from P between PE and PE plus delta P. So let's say PE was 324, and this is the 93 steps. So 0.93 times 380 kilonewton in our calculation, 353. So this is the, if I subtract 324, then it will be 29 kilonewton. This is the delta P that we can apply to this structure. 29 divided by 324. So it will be around 10%. So we can apply this load. It's still stable. And after that, it is not in equilibrium anymore. It loses its stability. But if you solve it by linear material, then you will not see this because it is not considered the material effect. Yes, that is the end of this example. And thank you for watching. I hope that now you are more familiar with the post buckling, and also a little bit more about how to model it in the PEM software. Thank you and see you in the next video.